When you have a data set, one of the first questions we ask is, well, what is the average value of the data set? And when we ask that kind of question, it's looking at the whole data set, and it doesn't really consider specific values. So we're going to take a look at specific values today and ask the question, how far is a specific value from being average? And underneath this, there are two sub-questions. The first sub-question is, how spread out are the data values? There are two ways that we can measure the spread of data. The first way is through what is called the range of the data set. And the range is simply put going to be your max value minus your minimum value. For example, if we were to look at our small data set that just has the 5 values 5, 5, 5, 7, 8, the range of this data set would be 8 minus 5, our largest value minus their smallest value, or 3. So it has a range of 3. Given the definition of the range, then, we observe that, like the mean, the range is influenced by extreme values, or what we call outliers. A second way to measure how spread out data is through what is called the standard deviation. We will develop the formula for the standard deviation using our small data set, again, the 5 values of 5, 5, 5, 7, 8. Recall that this data set had a mean of 6. So to answer the question, how spread out are the data values, or more specifically, how far is a specific value from being average, an initial thing we might do is calculate the plane deviation that every value is from the average. So we'll create a table with our data values and then the deviations. So we have our data values listed, and now we're going to calculate the deviation each value is from the average. 5 minus 6 is negative 1. 7 minus 6 is 1, and 8 minus 6 is 2. So the formula that we have for this really is x, where x is our specific value, minus x bar, the average. Now if we were to sum up these values that we have right here, all of the deviations, to get an idea of the overall deviation of this data set, we would find that the sum of x minus x bar is 0. Well, that doesn't really help us much. The problem is, by definition of the mean, the negative values will cancel out the positive values. So what can we do instead? What we can do is we can try to make all of these deviations positive. And one way to do so is actually to look at not just the deviation from the mean, but the deviation from the mean squared. So we take all of these values and we square them. 1 squared is 1, and 2 squared is 4. So what we have in the second row then is the square of the deviations each data value is from the mean. If we wanted to get an average of these deviations squared, we would think about adding all these values up and then dividing by the number of data points. So it makes sense for us to at least consider that. So we would add up 1 plus 1 plus 1 plus 1 plus 4. And if we wanted to get the average, we would think about dividing by 5, because that's the number of deviations we have. However, for reasons we won't get into in this video, since this is a sample, we will divide not by 5, but by 1 less. So we'll divide by 5 minus 1, or 4. So this gives us 8 over 4, or 2. This value of 2, however, is not the standard deviation. This right here is what is known as the variance. Remember how we had squared all the deviations back up here? The standard deviation attempts to take that into account. And so what we're going to do is we're actually going to take this value, what we call the variance, and we're going to take the square root in attempt to cancel out the squares we initially did. So the standard deviation is equal to the square root of the variance. In this specific problem then, it would be the square root of 2, which is approximately 1.41. So there's some notation that we want to introduce regarding the standard deviation. If we're dealing with the standard deviation for a sample, it is represented by the lowercase letter s. If we're dealing with a population, the standard deviation is represented by the Greek letter sigma. For the most part, we're going to be working with the sample standard deviations when we have to calculate things by hand. Now, let us come up with a formula so that we understand just what we did in all of the steps above. The first thing that we had to do was we had to remember what the average of our data set was. So that's really going to be step 1, calculate your average. Step 2 is to calculate the deviations from that average. So we calculate all these individual deviations here. Step 3, we square them. And then step 4, we added the squared deviations up and divided by n minus 1. So we are looking at the Greek letter capital sigma represents to sum up. We are looking at x minus x bar squared, the sum of all of those over n minus 1. And this formula represents the variance. But recall, the standard deviation is the square root of the variance. So the sample standard deviation is given by the formula the square root of the sum of x minus x bar squared all over n minus 1, where again, as a reminder, n represents the number of data points. In general, it's easier to let a calculator actually compute the standard deviation. The one thing to make sure when you do so is to get the sample standard deviation rather than the population standard deviation. One thing that we should ask is, so what does the standard deviation tell us? There are 2 responses. The first response is, the smaller the standard deviation, it implies the data values are closer together. And so obviously a larger standard deviation implies that the data values are more spread out. In other words, smaller standard deviation is more consistent data values. A second thing that the standard deviation tells us is the standard deviation gives us bounds on how far from the mean the data spreads. A famous Russian mathematician named Pafnuty Chebyshev concluded the following result. He discovered that let k be any value greater than 1. Now, take any data set. So for any data set, at least 1 minus 1 over k squared. This number will be a fraction of the data values are within k standard deviations of the mean. This result is extremely useful because it gives us bounds on how far from the mean the data actually spreads. And it applies not just to some data sets, it applies to any and all data sets. We know how much of the data has to be within k standard deviations of the mean. So let's consider some examples of this. So to begin with, what percent of data values lie within 2 standard deviations of the mean? Here we see that we want to know things about 2 standard deviations of the mean. So that means that k is equal to 2 in Chebyshev's theorem. So according to Chebyshev's theorem, at least 1 minus 1 over 2 squared, which is equal to 1 minus 1 over 4, or 3/4, or 75%, of the data values are within 2 standard deviations of the mean. So at least 75% of your data values are always within 2 standard deviations of the mean. Don't believe the Russian mathematician Chebyshev? Well, let's actually test it out using our large data set. Again, those are the 10 values from 49 up through 76. We'll start by creating a number line in which we list our average. And then from here, I want to count 2 standard deviations to the right. So I want to look at x bar plus 2s, and I want to count 2 standard deviations to the left. So I want to look at the value of x bar minus 2 standard deviations. Now for this large data set, the sample standard deviation was approximately, if you used a calculator, you would get 8.517. So if I look at my average of 64.1 plus 2 sample standard deviations, right here I get a value of 81.1, and if I look at my average minus 2 sample standard deviations, right here on the number line, we get a value of approximately 47.1. So the question that we ask ourselves is, from our large data set, remember the values range from 49 up through 76, how many of them fall in the interval from 47.1 up through 81.1? Well, all of them do. So 100% of our data values are within 2 standard deviations of the mean. What were we guaranteed by Chevyshev's result? We were guaranteed that at least 75% of them would be. 100% certainly matches that criteria. In other words, Chevyshev's result is true here in this example, but it's actually true for any data set.